All right. So what remains here is really very, very simple, right? We want to evaluate the derivative of the strain with respect to the electric field. We could have done this by differentiating in the equation of states that we have done in the past, etc. We can differentiate in several ways, as we know. But okay, this time we are going to do it slightly different. We have here the expression for the strain as a function of the polarization, and we can take the derivative here directly, right? So I am interested in this guy. Okay. This expression, by the way, is totally general for any value of the electric field applied. Remember the way we derived this expression from the equation of a state for the strain. There was no electric field there explicitly, and this equation is absolutely general. Of course, the action of the electric field will be felt in the polarization. That's what will inform the strain about the electric field in this model, the change in the polarization. So indeed, when we take this derivative, what do we get? 2 times B over C, P, and the derivative of the polarization with respect to the electric field. Makes good sense. And this derivative is nothing else but the electric susceptibility, which we have already examined, right? So this would be epsilon 0 chi multiplied by the polarization itself. Okay, totally general expression. Things to comment here. Well, not surprisingly, the effect of the strain will be stronger when the susceptibility itself is stronger, right? I mean, so essentially, the more reactive our material is to an electric field, because the polarization changes the most, the more we will feel it in the strain. Okay? Also, not surprisingly, something that maybe you know from general considerations of symmetries in crystals, this piezoelectric response will be different from zero as long as the polarization itself is different from zero. So this expression is telling us that in the paraelectric phase, where the P is equal to 0, there will not be any piezoelectric response. Okay? Is that easy to see? Is that easy to see? No, it is. It is easy to see from the point of view of symmetry, because if you imagine, now for a second, in a parenthesis, that I write the strain, I want to write the strain as some sort of spontaneous strain. Imagine I have a system where I can create a polarization little by little, by hand, almost taking by hand, moving the polarization, and then I let the system relax to see what the strain, how a strain reacts to that, right? So I can write the strain as the strain when there is no polarization. This is going to be 0 according to our theory, by the way. And then I can write here maybe a term A1 multiplying polarization, a term A2 multiplying polarization squared, etc., as a Taylor series. Like I'm creating a small polarization. And one thing that we would get convinced very quickly is that, well, we have seen already, is that the strain cannot depend on the sign of the polarization. So meaning that, if you remember, the same kind of arguments that we did to convince ourselves that this is the lowest order coupling kind of convince us that in our simple model crystal, this state with P up and this state with P down, both of them will have an expansive strain to accommodate the development of a polarization, but in both cases, therefore, the strain we expect it to be positive. So the strain cannot depend on the sign of a polarization. So in this expansion, and we could see this from symmetry using other arguments, but the odd terms in the expansion are 0 by symmetry. Okay? And so the strain has to go like P squared. Okay? And now the derivative of strain with respect to polarization, if you want, which is very similar to the derivative with respect to field, has to go like P. And so the derivative of strain with respect to polarization depends on P. If P is 0, the derivative is 0. That's what we are seeing here with the electric field and with an intermediate chain rule. Okay? But this is essentially this symmetry. So indeed, we have piezoelectric response only in phases where the polarization is developed, according, at least in the realm that this model can give us. Conversely, in all ferroelectric phases, we have a piezoelectric response. All of them have non-zero polarization, all of them have the electric susceptibility, so all of them are piezoelectric. Okay? So that's another piece of physics that we have there in that expression. And the last thing, maybe, is to try to think about the temperature dependence of this thing. Right? To think about the temperature dependence, well, here we have to be a bit careful, right? Because essentially, Tc, we have here the product of two quantities that are temperature dependent themselves, right? We know the polarization does something like this in this kind of model. This is the polarization. And we know that the susceptibility does something like this in this kind of model. So the susceptibility diverges at Tc, and the polarization goes to 0 at Tc. So if I think about the product of those two, well, above Tc is clear, is 0. This is D. But below Tc is not so clear, right? I mean, so essentially, when we are getting to Tc, what is it? Is it does it go to 0? Does it go to a number? Does it go to infinity? And to figure that out, we need to plug in here the explicit temperature dependencies that we can also compute for chi and for p. Okay. So again, this is something that we have already done. Hopefully, without making any mistake, I can write that p. If you remember, p square equilibrium was something like, let me remember, alpha prime Tc minus T over beta. We got an expression like this. Now here we have to be careful. If we do the math, it's going to be exactly as we solved in a previous lecture, but instead of beta, we are going to have beta tilde. Okay? But otherwise, everything is going to be exactly identical. So we have that. And for the susceptibility, if you remember, the susceptibility was the inverse of something we called the curvature. The curvature was something like this, T minus Tc plus 3 times beta p squared. Here, it will not be beta, it will be beta tilde. This is to the minus 1. And of course, to resolve this one, we need to plug p equilibrium there. So all in all, if I am not making mistakes, this is going to give us, let me write it like this. 3 times, this is with a minus, so 2 times Tc minus T alpha prime. If I'm not making any mistake. And then when we put everything together, what do we have? We have that D will be 2 times V over C epsilon 0 squared, which is 1 over 2 times Tc minus T alpha prime. P equilibrium, let's take the positive polarization, and that gives us the square root of alpha prime Tc minus T over the square root of beta tilde. So we have a complicated prefactor. Let me make room. but the temperature dependence is quite clear, right? So from here, D equals minus 2 goes away with the 2, so B over C square root of beta tilde. What a terrible thing. Times alpha prime, also inside the square root. And then we have here Tc minus T to the minus 1 over 2. Okay, so we have a square root of the temperature difference in the denominator, so D with a negative sign there, but B is a negative number, so D does something like this. It diverges close to the Curie point because the divergence of the susceptibility wins over the polarization going to 0. Again, very, very interesting because this literally means that if we had a ferroelectric with an ideal second order phase transition and we get close to the Curie point, we have there extremely good piezoelectric, so good that we have a material where an infinitesimal change in electric field in the environment gives us a finite elongation or contraction. Okay, so extremely important if you want to make a sensor, etc. The converse effect would be the one in which, of course, with a very small strain or very small stress will give you an electric signal. That one is also going to diverge, and that would be very good if, for example, you want to make a microphone where you are transforming pressure waves into electric signals, or a sonar, or whatever. Okay? Everything was in our very simple theory, and it's kind of remarkable that only hypothesizing this, well, figuring out that this is the simplest symmetry allowed term and the sign of B from very simple arguments, we actually get the whole physics of the, not the whole physics, but the main physics of the piezoelectric response as it applies to most ferroelectric materials in a pretty straightforward manner, almost as a thought experiment. All right, questions?